Good evening, everybody, and welcome. My name is Holger Dulin. I'm a professor in the math department here, and I have the honor, was given the honor to introduce Tadashi. Before I do that, let me acknowledge that the university land is traditional land of the Gadigal people of the Aora Nation, and we pay our respect to their elders, past, present, and emerging. Tadashi Tokieda. It is a difficult job to introduce somebody like him, but I at least have known him for a long time, somewhere between 25 and 30 years, when we met in the UK. Tadashi had done his PhD in Princeton and was kind of on the way to Trinity College in Cambridge, and we were both working on mechanical systems and toys, in fact. And Tadashi has never lost his interest, passion for understanding toys and understanding mathematics through toys and understanding toys through mathematics. I try to do more serious things, but he actually stayed and kept his passion up, and that is so amazing that he made a career out of this, right? So he is actually a philologist. He has learned many languages, and I remember actually maybe around the time when we first met, I learned from him that the cat says meow in almost every language of the world, and that's not so for dogs or frogs or other animals. Why is that? I don't know. But soon we started to talk about mathematics, and he has written many amazing papers, and the titles of these papers are maybe the most amazing thing when you read them. For example, A Golfer's Dilemma. This is about how a golf ball can roll into the hole and actually come out again, which seems impossible. He's written papers on spinning tops. And what was the French title? Dancing vortices. Sorry, I'm saying it in English. Anyway, it's a long list of very interesting papers. But let me tell you a tiny bit more about him. So after Cambridge, he went to Stanford and is a distinguished professor there, and of course he's a mathematician, but his expertise is really in communicating mathematics, and I think it's not even correct to say he's giving talks, and you will see. I mean, his talks are not usual math talks at all. Actually, he gave a colloquium earlier, and I would say that was it's like a firework in a way, but it's an extended firework for 50 minutes. And his talks contain demonstrations, and there will be plenty of them here. So let me stop and hand over to him, and he will explain how to make a world from a sheet of paper. Please welcome Tadashi Tokieda.
I'll start from the beginning with a magic show. I brought here a coaster which is round and a little piece of paper in which I put the hole, drilled out the hole, and watch carefully. I can pass the disc, the coaster, through the hole. It is really going through, yes, and then it is going through, and yet when you open one next to the other, it's clear that the diameter of the disc which is passing is larger than the diagonal of the hole. I'm not stretching, let alone tearing anything, and yet it does really go through. Yes, it's going through. I haven't started cheating yet, so it can go back and forth. It's really going through the hole. How come that the small hole can let a larger than itself object pass? It is really peculiar, no? I could have stopped my talk there, but because you seem to be such a nice group of people, I'd like to give away the secret for free. Usually at this point I start passing around the hat, but you see, when you fold the paper like this, yes, and then just like the flat, there's a gap here which I can take advantage of to pass things through. But this gap used to equal the diagonal of this square. okay? But that's not all I do. Having folded this paper, I grab those two things and then start twisting the paper. And as I twist, you see in the camera that the middle of the paper starts rising. And until those two sides align, and then I squash. Having done so, I have created a gap here, this wide, which used to be, if you track back, not the diagonal, but the sum of those two sides. And if you remember Pythagoras, I have gained the square root of 2, that is more than 40%. So in doing so, I can pass this thing, the secret being that I should make a hole whose diagonal is shorter than the diameter, but whose sum of the two sides, I have 40% more room, is longer than the diameter. And what we are seeing here is actually a very, very interesting principle of general nature. So passing trick, what seemed impossible becomes possible. Why? How? Because I allowed myself to escape into the ambient extra third dimension in which we live. If you were stuck on the 2D, then we couldn't have done it. We tend to think of paper, membrane, surface of any kind as two-dimensional, but what message I'm sending to you is that it's actually very important to think of them as living, thriving, and surprising us in the ambient 3D. It is the interaction between the 2D, which is intrinsic, so to speak, to the sheet, and the 3D, which is extrinsic, which has to do with the ambient space, which will be the leitmotif of this talk. Do you recognize this person? He looks very romantic, and indeed, he's one of the most romantic figures in the history of mathematics. Does anybody recognize him? Galois, thank you. So Galois is a Frenchman who died at the young age of 20. And if you do the subtraction, you might think that I can't do the arithmetic because 32 minus 11 is 21. But he died shortly before his 21st birthday in a duel. And he left a gigantic legacy for all of us to chew on. Galois theory, Galois representations, that those are the household terms. And really, in the 21st century, we're still working on directions that were started by Galois. And one of the things that he taught us to solve very easily goes back to the Greeks. The Greeks had many problems, but one of the famous problems is the following. With ruler and compass alone, straight edge and compass alone, you might have used these things in school. Can you divide an arbitrary angle into 3 equal parts, trisection of an arbitrary angle? Bisection, that is, in 2 equal parts, is very easy. Yeah? So you have an angle. Can you draw a line which divides this given angle into 2 equal parts? You can do that with a ruler and compass. There's a classic way of it. But can you do the same thing into 3 equal parts? To be sure, there are angles that can be divided into 3 equal parts. For example, 180-degree angle, 60, 60, 60, that's easy to construct. But that's not the question. The question is, does there exist a universal algorithm with ruler and compass alone, which, given an arbitrary angle of your choice, allows me to divide that into 3 equal parts? And Galois says that actually no. An angle that looks as innocuous as 60 degrees is impossible to trisect. In other words, you cannot construct a 20-degree angle with ruler and compass. You cannot, however clever you are and however hard you work. It's impossible. You can prove that it's impossible. However, there is a great Japanese traditional art of origami. Ori means folding, and kami is paper, so literally folding paper, which is becoming more and more popular, not only as an art form, many children and adults alike create wonderful forms, but also in engineering. Origami engineering is one of the things. And with origami, it turns out that you can trisect an arbitrary angle. So let me show you. First, let's start with the easy case of bisection, dividing into 2 equal parts. And imagine that your angle, the angle that you want to bisect, is given as the corner of a sheet of paper. Yes, the corner of a sheet of paper is usually 90 degrees, but imagine a sheet of paper whose corner is that angle. Okay. How do you bisect it? Well, nothing simpler. Anybody will think of folding the paper in 2, half, and then align those edges. And once they're aligned, you crease that part on the right. And when you open, you have a beautiful crease line, which is coming out, which is the bisector of this angle. Sure. Trisection is no harder. What you do is to fold over, and then you overshoot and fold back. So you have those 2 flaps, if you like. And then when you align the blue and red parts, gradually you have to negotiate. When they're aligned, you just crease the whole thing, and when you open, you have 2 beautiful creased lines that are coming out, and those are the trisectors of the angle. And end section, if you like, into end parts, it's no harder. You go back and forth, you create end flaps, you negotiate. You may not like this term, negotiate, but you just keep arranging. And when successively you come to the right sort of arrangement, you just crease and you have end fold. So it is completely general. Okay? So origami is rather powerful. Do you recognize the next person? He looks rather grumpier than the first one, but it's no less great a mathematician. Do you recognize this portrait? Gauss, that's true. So he lived a longer life, Carl Friedrich Gauss, and he stands as a giant between the 18th and 19th centuries. Many of the directions in modern mathematics that we are still working on were started by Gauss and were put a lot of content by Riemann and later on. Anyway, so he also is really one of the inspirations for all of us who are working in mathematics. And one of the Greek problems that he allowed us to solve is this. You might have had the experience of drawing a regular polygon. Yeah? So regular trigon is usually known as the equilateral triangle. Regular fourgon is a square. Regular pentagon, regular hexagon, you start running out of your knowledge of Greek prefixes, so you say regular sixgon, regular sevengon, and so on. Anyway, so which regular n-gons can you draw by ruler and compass alone? Yes. So here I gave you a construction of regular trigon, that's an equilateral triangle. You just draw a segment, and you plant a pivot of the compass on the left edge, left end point, and then you just draw a circular arc, and then you do the same on the other side. And where they intersect is the point which connecting to the remaining to the end points creates a regular trigon, an equilateral triangle. Okay, so this works. How about regular n-gon? It turns out Gauss taught us to think this way, and you can solve this problem. If you go to a great university like University of Sydney and learn mathematics, in the second, third year, you can learn this, that actually n, which can be constructed like this, has to be a very, very peculiar form. So first, it's a power of 2. That's actually cosmetic, so forget about it. The essential information is as follows. You take primes, yeah, those numbers that don't have any non-trivial divisors, of the form 2 to 2 to some n plus 1. Those are called Fermat primes. And if you plug in various values into small n, 1, 2, 3, 4, and so on, you get this sequence of numbers, 1, 3, 5, 15, 17, 51, 85, and so on, so on. And those, among those, the primes are colored in boldface. So 3, 5, 17, 257, those are primes. So if you take those primes, Fermat primes, and distinct ones and multiply them in any fashion that you like, yeah, and however many you like, and that's the result is the n that can be constructed by ruler and compass as a prime as a regular n-gon. Okay, and powers of 2 is easy because once you have constructed, let's say, a regular 5-gon, it's easy to divide each of the angles into 2, so you can double the number of sides. So doubling is really cheap. So any power of 2 you can stick in front without any extra effort. Okay, so it is that. So n has to be a very special form, but probably you're beginning to suspect already. With origami, you can do O n. So let's try to do this. Before doing that, I'm going to give you a little demonstration for n equals 5. I'll show you how to make a regular pentagon. Now, 5 was one of the Fermat primes, so it's not so interesting. But this will show you how to do it in general. Okay? I'm going to make a regular pentagon, regular 5-gon. Take a strip of paper and tie the simplest knot that you can imagine, like so, okay? And having tied this knot, you just keep tightening it, and flattening it, and just keep doing it very delicately and very carefully, but without thinking anything. Just empty your mind and keep tightening the knot. And eventually, you get a completely flat, tight knot like this. Now, there are parts that are sticking out. I don't need them, so I'm going to throw them away. And I'll show you what's in the middle. What you created in the middle is a perfect regular pentagon. I'm glad you liked it. I like it too. I mean, I didn't do any work. I didn't use any intelligence. Nature took its own course. It is really beautiful. Now, this is a really beautiful thing because we humans have limited ability, but we just ask nature to make something for us, and nature obliges. Now, if you are lucky enough to visit Japan, I'm now speaking on behalf of the Japanese Tourist Bureau, and then stay at one of those traditional inns called ryokan, they lend you a beautiful sort of pajama called yukata, and on a nice summer's day, it's nice to go out on stroll and then look at the festivals and the fireworks using yukata. But to go with yukata, they also lend you a soft belt made of cloth, and then it's traditional to fold this long sort of belt in a pentagonal pattern and offer it to guests. So this has been known in Japan for quite a long time. Now, it is possible also to make regular n-gons, regular, to be precise, odd gons. So I have done regular 5-gon. How about regular 7-gon? Yeah, the next odd number up. Here's how you do it. For n equal 5, regular 5-gon, I took a strip of paper and I tied the simplest knot, the knot which passes through itself once, shall I say. Suppose that now you make a knot that passes through itself twice. How? I'm going to show you a picture in a moment. That's the next one up in complexity. And having tied that knot, which passes through itself twice, and you flatten and tighten, flatten, tighten, and what appears then automatically is a regular 7-gon. If you have a knot, start from a knot that passes through itself 3 times, you get a regular 9-gon, a knot of 4 times, you get a regular 11-gon, and so on. So you can access all the odd numbers. And having accessed all the odd numbers, it's easy to double all the sides, so you can access all the even gons, okay? So what you are seeing is a remarkable phenomenon. Excuse me. So here, I have drawn a picture of regular 5-gon, and next to it, to the left, is regular 7-gon. Okay. So how do you visualize this? This is the pattern. Imagine that you have already drawn a regular 7-gon, yes, and the inside regular 7-gon is coated by mirror. And you go in there like a ray of light, which you all are, and you bounce off the mirror, boom, 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 and you come out. That order in which you're bouncing, boom, 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 you keep track of which line went first before which other line, and that keeps track of which strip has to come above the other strip. And if you obey that order and then just make a knot according to that pattern and flatten and tighten it, you get regular 7-gon. Okay? So a knot with 1 pass will give you n equal 5, 2 passes n equals 7, 3 passes n equals 9, 4 passes n equals 11, and so forth. But you're going to say, wait a minute. There's one odd number that's missing, regular 3-gon, n equals 3. Knot of 1 pass already gets you to n equals 5, 2 passes n equals 7, 3 passes n equals 9. So how many passes should the knot have in order to access n equals 3? What's your idea? 0. Yes, that's the one. So you go in and you try to make a knot, but you don't succeed, and you come out, and in that corner, you have a regular 3-gon equilateral triangle hiding, as you can see. So you can actually do all n. As I said, bisection after that is cheap, so really you can successfully make regular n-gons with origami for all n. Isn't that wonderful? So origami is really a powerful way of doing geometry, and we shall continue this. Now, I'd like to give you a present today, because you have been so kind to come to my lecture. I came all the way, by the way, from California, so I have been kind to you too, but maybe you haven't. But anyway, so speaking of kind, this is a lion that I folded, and when I unfold it, you have this kind of pattern. Yeah? Don't pay too much attention to blue and red. These are ridge and valley folds. But what I would like to note is that this is, if you like, a whole bunch of points and lines. Mathematicians like to talk about the vertices and edges. So please forgive me if I talk about vertices and edges. I mean points and lines, okay? So some of the vertices have 4 edges that are assembled there. For example, 1, 2, 3 there, okay? I'm pointing to this. Some of the vertices have 6 edges that are meeting there. Some of the vertices have 8, as many as 8 edges meeting. But you see, it's always an even number. And it is a theorem that around each vertex that you get by folding a sheet of paper into an origami and squashing onto a plane, this lion, whether it likes it or not, it can be squashed onto a plane. And if you unfold it, you always have, around each vertex, an even number of edges. That's a theorem. But that's not the present I would like to show you. So it's, please just accept it. It's not too difficult to prove. And for those of us who are overeducated, I can say that, well, when you squash it, you are creating something that you might think of as a singular covering space. And as you squash, you have front and back of sheet, and so on. That kind of pattern forces the parity, okay? So it's always an even number. But so the simplest pattern looks like this, yeah? That is, you have 4 edges that are coming together, and that's going to create 4 sectors, angular sectors, whose angles are as shown. So let's start with an experiment. The simplest way to do this is what origamists call the square fold. I can just do this, I can do this, and then you have square patterns. And this is something that you use every day for practical purposes. There's a little bit of glare, so I'm going to trace the folds so that you can see. 3 of the folds are ridge, and one of the folds is valley, but that's not our concern. So you see, and it's 90 degrees all over the place. Yeah? But that I had to do rather carefully. If I don't do anything carefully and I can fold at random, I get a pattern which looks a bit like this. Okay? And I'm going to trace the pattern like that. Okay? Like so, like so, like so. Okay? And I'm going to fold it again. Sorry, I should like to do it a little differently. Let me actually do it in another fashion, because I said randomly, but I would like to do it beautifully randomly, not randomly, if you see. It's a difference between known unknowns and unknown unknowns. Anyway, so this is what it is, okay? All right, so, by the way, which part, oh, this is reflected. So I have to actually draw everything upside down in the mirror reflection. So, okay, so let's say this is the angle alpha. No, it doesn't look like angle alpha. So it's this alpha, that's right, okay? And then this is beta, gamma, and then, remember, this is not just mirror image, it's upside down for me. And this is delta. Okay. So, if, as you have just seen, this is made by crumpling a sheet of paper or doing origami and squashing, it turns out that those angles cannot be arbitrary. Okay? There must be some relationship among those angles, and the relationship is, one of them is as follows. First of all, they have to add up to 360 degrees. You wish you had said it first, but I did. Okay. that's the easy part of the theorem. But the hard and the interesting part of the theorem is that opposing angles, that are facing angles, must have the same sum. Alpha plus gamma equals beta plus delta. So I'm going to show you here, this plus this, alpha plus gamma, must equal beta plus delta. Okay? In particular, if you have a picture like this, that configuration cannot be created by folding a sheet of paper, however clever you are, however hard you work, because the angle of that narrow wedge plus the large sector is far too large compared with the sum of the other two. Okay, so it just violates one of the conditions. You cannot do it by flattened crumpling. This theorem goes back to Kawasaki, but actually there's some earlier work by a physicist called Fushimi and so on. This is kind of folklore theorem in the Japanese community, but that's the necessary and sufficient condition. Now, I'm going to give you a present. Present is usually an object which might be heavy, it's breakable, costs money, and when you go through airport security at the Sydney airport, they give you no end of trouble. But the present that I brought you here today is a phenomenon, or if you like, a math theorem. Yeah? And this phenomenon, intellectual phenomenon, costs $0, yeah? And weighs 0 grams. It's totally unbreakable, and when you go through airport securities, they are no wiser. Okay? And moreover, you can keep sharing it with people, and it becomes better and better. So I'd like to share with you this present that you can take home, indeed. So I would like to prove that alpha plus gamma equals beta plus delta. Okay? In order to prove this, let's go back to where it was. Okay? So this is beta. Okay? And so if you turn around and look at this angle, that's beta. But beta is the overlapping version of alpha and gamma. So what's the overlap, the excess overlap that I'm adding? It's delta. So alpha plus gamma minus delta must equal beta. That's exactly the same thing as saying that alpha plus gamma equals beta plus delta, QED. Okay. So that's the theorem. And it's a theorem that could have discovered a long, long time ago. It's amazing, isn't it? So in general, I say that each vertex has to have an even number of edges coming together. So even valency, if you like, in chemistry terms. So let's call those angles alpha 1, alpha 2, all the way to alpha 2n. Okay? Now, those angles are realizable by flattened crumpling if and only if those two conditions are satisfied at the same time. First of all, they have to add up to 360 degrees. That's obvious. But second, not the sum, but what we mathematicians like to call alternating sum. That is, plus alpha 1 minus alpha 2, plus alpha 3 minus alpha 4, plus minus must close to 0. it's easy to rewrite the 4-angle case in that terms. Instead of saying alpha plus gamma equals beta plus delta, I could have said alpha minus beta plus gamma minus delta equals 0. Yeah? It's the same thing. And it turns out that if these are satisfied, you can realize those numbers by crumpling a sheet of paper. So what I mean is as follows. Suppose that, for example, Professor Tillman gives me a bunch of real numbers, positive real numbers, that add up to 360 degrees. And of course, he's not going to give me them in the right order because he's a mischievous character, so he's going to jumble them up. But if I can find a rearranged order of these angles so that the alternating sum becomes 0, closes 0, then I'm in luck. What I do is, among all those numbers in that order, yeah, I find the largest of those, and starting from these, I start folding forward and backward and forward, backward and forward, backward. Okay, I keep doing this, yeah, according to that angle. I forward by that angle, forward and backward by the next angle, forward by the next angle, and so on. And when I run out of the supply of angles, I know that I close exactly where I started because of this closure condition. And then, having done this, I crease the whole thing and open, and you see those beautiful crease lines that are coming out, which realize the angles given by crumpled sheet of paper. So this is the same proof as before. And I kept saying closes 0 because this is in mathematics, in the area of mathematics called topology. It's the discrete analog of homology. It closes in the sense of closed form. It's a closed manifold and so on. Yeah. So this is the theorem. So far, we have been playing with mathematics, more particularly geometry, but we shall now transition to physics gently. And afterwards, we take off and start subtly and imaginatively start going away and expand our area of investigation to engineering and physiology and even medical devices and so on. And we have to expand our field of investigation because the phenomena that we're talking about exist across all scales in the universe. For example, in the top left corner, I show you a picture of a paper, which is from the region of Mino. Mino paper, Mino kami, goes back 1,000 years in Japan. So what it is that you take a sheet of paper, ordinary sheet of paper, and then, interestingly, you wet it and crumple it completely. And then, having crumpled it, you take a cut persimmon. You know that fruit, which is a national fruit of Japan, it's called kaki. And then, with that surface, you scrub the paper and you stretch it out again. Yeah? And you keep scratching. And that sort of entangles the fibers and then sort of puts some of the essence of the kaki into it. And then after you do that, you dry the whole thing in the sun. And then having dried it, you wet it again and crumple, and then you stretch it again with the kaki. You keep doing this over and over. And that turns out to make the paper so strong and microfibers get entangled so finely that you can make from this paper things like bags, clothes, even shoes. Yeah? And it goes back 1,000 years. And everything's happening on the scale of less than a millimeter, so it's really small. Top right corner, you see one of my friends, and you see that its trunk is lined with lots and lots of wrinkles. They are the best biomechanical and thermal reasons why nature likes to take advantage of wrinkles, and this is one of them. And that's happening on a scale of centimeter to meter, let's say human scale, our scale. Yeah? And also, nature can play origami on a gigantic scale. This is a map, if you like, of view of Latin America. And its backbone, the Andes Mountains, a gigantic range of mountains, which extends for about thousands of kilometers. And what is that? Well, Latin America is a continent. And then there is the Pacific continent, the Pacific plate. Pacific plate is technically called the Nazca plate there. And what happened is the Pacific plate started pushing against the continental plate. And then what happens when one thing pushes against another on a sheet of paper, which is the crust of the Earth, it starts rising, as in the magic show. And that rising in between is Andes Mountains, okay? By the way, I cannot help digressing in this lecture, so please bear with me. You know that the Amazon, which is the greatest river in terms of the water flux, okay, there are rivers that are longer, for example, Nile, but in terms of the water carried, Amazon is by far the greatest river on Earth. And all of you know that the Amazon starts in deep Brazil and flows into the Atlantic. Do you know that the Amazon used to flow into the Pacific? Because the Latin American continent used to tilt the other way. And it was flowing to the Pacific, but then Nazca plate kept pushing, and they started rising. And at some point, the entire continent ended up tilting the other way, so the Amazon started tilting, going into the Atlantic. Isn't that amazing? And it's fairly recent on geological time scale. Anyway, so all these are happening across all scales throughout the universe. And depending on whether the crumpling and so on is happening on designated way or random way, it comes under many names. For example, designated one is origami. random one you would call crumpling, and in between there is the really unit, if you like, the fundamental phenomenon of buckling. Buckling, I mean this. If you take, for example, a little rod, here ruler, and if you start compressing the ends, pressing the ends together toward each other, well, you think that nothing is happening, but actually the entire thing is becoming shorter a little bit. It's compressed. It's acting elastically. But at some point, at critical load, I'm pressing, the whole thing cannot take the load anymore. Boom, it bends like this. Boom, it bends like this. And that's called buckling. Suddenly there's a large deflection. Until then, it's very, very tiny infinitesimal compression along its length, and this buckling. And indeed, all these phenomena that we are mentioning is in some sense a combination and variations on buckling, combined bucklings and so on. Now the challenge is, can we find any science, any piece of mathematics that's behind this wide diversity of phenomena, including the random case? For example, here you have the impression, don't you, that you are seeing a photograph of a crumpled sheet of paper. Well, for the good reason that it is a photograph of a crumpled sheet of paper. But then, if you ask an artist to draw a crumpled sheet of paper, you'll find that almost no artist is capable of drawing a convincing-looking crumpled sheet of paper. I checked Leonardo da Vinci. He cannot draw a crumpled sheet of paper. Whereas we, who have lived this universe for long or short periods, we all instinctively can see what looks like a real crumpled sheet of paper. So let me make it even more precise. You see, crumpled sheet of paper, if you just crumple and squash and open, is just like those dots and lines that we studied before, right? So vertices and lines. So you can draw lots and lots of vertices and edges. This is called a graph in the sense of graph theory, or network, if you like. You can draw lots of networks on a sheet of paper, but most of them do not come from crumpling a sheet of paper. For example, at each point, you have to satisfy this alternating angle is equal to 0, alternating sum equal to 0, right? But anyway, so the question is, among all the possible networks that you can draw on a sheet of paper, which ones are realized, which ones are really a result of crumpling a sheet of paper? And what is remarkable that we humans instinctively can recognize. So our brain knows, but we cannot take out what we know. It's all in the subconscious. It's all in the intuitive recognition. So what we would like to do is, what is it that we are recognizing? What is it that we are seeing when we see a crumpled sheet of paper? What's the science? We want to bring it out to the explicit. We want to bring it up to the conscious level. So to do this, we need this person. Do you recognize this person? He's less famous than the previous two. Do you recognize somebody? No? But although he's less famous, and he looks rather happier than the previous two, he's Simon Denis Poisson. You run into him all over the place when you study mathematics or physics or engineering, because you study Poisson's equation, you see Poisson bracket in quantum mechanics, you see Poisson distribution in probability Poisson this, Poisson that. And what I would like to tell you about is what is called the Poisson ratio. Now, there is a branch of physics, engineering if you like, called theory of elasticity. Elastic bodies, solid bodies. And this involves two basic numbers. So my purpose is to teach you half of the theory of elasticity in 45 seconds. Here we go. So take a piece of material, block material, and you squeeze it in one direction. What do you think happens to the body of material? Of course, it's going to bulge out in the perpendicular direction, transverse direction. And if you pull in one direction, of course, it's going to thin its girth in the perpendicular direction. That ratio of how much it bulges out per how much I squeezed in, bulge per squeeze, is called the Poisson ratio. Okay? So Poisson ratio is very important. It tells you, if you like, the material property that characterizes the transverse response to some direction. Okay? If you want to measure the longitudinal response, it's called Young's modulus. But anyway, so it's Poisson ratio. Now, for such an important central concept, which is used all over the place, unfortunately, there is no standard symbol, standard notation for Poisson ratio. Some people denote it by sigma, as you'll see. Some people denote it by lambda. God forbid, it should be Ramet constant. Kappa, or people who should know better denote it by p, oh my God, or pi. I mean, please save me. So there is no standard notation, which is a mess. But now, after many, many years of meditation in a Zen temple and so standing under waterfall and so on, I have finally discovered the God-given, or rather at least the Tadashi given, notation for Poisson ratio. which is this. So in 200 years' time, I would like the history of science to remember me as the person who finally found the right notation for Poisson ratio. Please adopt this with the alpha with the dot. You know that Poisson means fish in French, okay? So let's train our intuition. Suppose that you have this kind of strange pattern, if you like a rhombus or a losange. So those black dots are supposed to be universal joints, and then bluish, greenish lines are supposed to be rigid rods. Okay? So if you make a structure like this, and then compress it along the blue angles, the blue arrows, excuse me, of course it's going to expand along the red arrows, yes? So that's a transverse response to the blue compression. That's reckoned Poisson positive, and that already has an interesting property. If you assemble them into a structure, you get some mesh pattern. And if you make a dress out of this, it has the property that when you stretch it in one direction, it hugs your body tightly in the other direction. It's already interesting. And you can do the same thing with not just a quadrilateral, but with a hexagon. For example, if you assemble those hexagons into a pattern, you get some kind of honeycomb pattern, and it has the same positive Poisson ratio. Okay? To be honest, actually, Poisson ratio varies a great deal from material to material, from structure to structure. But there is one universal belief that permeates the subject, which is that the Poisson ratio should always be positive. That is, it's kind of absurd to think of a material where if you compress in one direction, in the transverse direction, it also shrinks. Yeah, surely that's not going to happen. And then you realize that actually there are some interesting materials that have almost zero Poisson ratio. So here's one example. If you take a spring and you ask yourself, well, if I compress it along the length, what's going to happen? Well, of course, spring will become shorter, but it doesn't look like it's getting any fatter, right? But if you look really precisely, actually it is becoming a little fatter in the transverse direction. So Poisson ratio is almost zero, but strictly speaking, if you're careful, it's actually still positive, okay? So it's very tempting in the face of all this to actually verify it in the literature. Yeah? And the greatest of authorities, that's Landau Lifshitz. So Landau was a wonderful physicist of the Soviet era who created single-handedly a great, great school of theoretical physics in Moscow. And it's really fantastic. And together with his student Lifshitz, wrote monumental 10-volume series called Course of Theoretical Physics. And if you walk into the office of any practicing theoretical physicist in the world, you see several volumes of Landau Lifshitz. That's the Bible status that Landau Lifshitz have. And it so happens that the volume 7 is denoted the theory of elasticity. I'm sorry that I brought out the French translation because that's my workhorse. I don't know why it's French. But anyway, here is a cartoon picture of Landau preaching to his students. You see Landau has some kind of angel-like wings, and there's a halo around it. The halo is all C because that's the wave function of quantum mechanics. And all the students have glasses and with donkey ears, and it says, "Thou Skazal," the master said. Anyway, so the volume 7. And there is a page which is very interesting, discussing Poisson ratio. And there's a footnote, which is a bit too small to read, so I'm going to translate it from French or Russian into English in real time. It says that actually the Poisson ratio varies only between 0 and 1/2, 0 and 1/2, okay? Positive and 0 and 1/2 only. We don't know of any body in nature for which sigma, that's their notation for Poisson ratio. But do you know a better notation for Poisson ratio? Thank you, it's alpha dot, right? Okay, anyway, so the Poisson ratio should be negative, that is, which will bulge out while being stretched. Yeah? So this is what the authority says, and this is really the consensus. But it becomes then absolutely natural to try to prove them wrong. And once you start doing it, actually, it's not so difficult. So structures with negative Poisson structure. For example, start with a hexagon, but now a dented hexagon. Concave hexagon, which is actually, it is a hexagon because it has 6 edges and 6 vertices, yeah? And if you compress that along the blue arrows, you can see that it will also shrink along the red arrows, yeah? To a certain extent. So that is negative Poisson. And if you assemble them into a structure, you can have some sort of cloth or something like that, mesh pattern, which has that negative Poisson ratio behavior. There are other ideas. For example, here you think that you have just a stacked version of boring squares, but they are joined in some interesting way, like this. So when you start opening, those squares turn left, right in alternation, and together, like a dance, when you stretch in one direction, it stretches in all other directions, and that's negative Poisson ratio behavior. You can do it with triangles, and also there are 3D versions. So I'd like to show you some examples of this. To start, this is some material, structure, which has positive Poisson behavior. When I stretch in one direction, it shrinks in the other direction, okay? And that's very, very intuitive. But this is, I'm going to go back to this, but please watch. I'm sorry about the camera. Please watch this. So this is a little ball which seems to be green, but when I toss it in there, it becomes orange. What? When I toss it in there, it becomes green, and so on, so on. You can keep changing color because what's happening here is that when I toss, I'm spinning it, so centrifugal force expands it. But when it starts expanding in one direction, because I'm spinning in this direction, so it just goes in the radial direction, but it expands in all directions at the same time. And when it expands in all directions, it just keeps going inertia and it snaps back into the dual configuration and then goes back and forth like this. So, okay, this is an example of negative Poisson ratio. Okay, so the truth of the matter then is not that the Poisson ratio is between 0 and 1/2. As Numberphile said. I'll try to defend them a little bit. But for isotropic materials, we'll focus our attention on isotropic materials. Isotropy means that in all directions, it looks the same thing. So it doesn't have any privileged direction. Yeah? For the time being, I'm talking about the material structures that look the same at each point in all directions equally, okay? Like a sphere, if you like. So for isotropic materials, Poisson ratio is not between 0 and 1/2, but actually between -1 and 1/2. So lower bound is not 0, but you can go all the way down to -1. And those two bounds have actual physical meanings. Let me interpret these, the upper bound 1/2. This is the limit of incompressible material, not to be confused with incomprehensible. So incompressible means that the material doesn't want to change its volume. So what happens? If you compress it in one direction, let's say by unit distance, well, it has two remaining directions into which it escapes, right? So it goes 1/2 and 1/2 in order to compensate for the -1. I'm taking the trace equals 0 because trace is the derivative of the determinant. But anyway, so this is what happens. So in dimension d, it will be 1/d-1, if you like, okay? So that's the upper limit, but the lower limit, -1, also has an interesting interpretation. That's the unshearable limit. What is a shear? Imagine a deck of cards, playing cards, and then you put them between your palms, and keeping the palms parallel, you just slide the palms against each other along parallel lines. So if you start with a deck of cards, it's usually a rectangle. But if you slide the top, it becomes a parallelogram. Yeah? That motion is called shearing. And it so happens that for isotropic material, Poisson ratio cannot be as close to, sorry, it cannot be -1 and cannot go certainly below -1 because that's the unshearable limit. It becomes totally unshearable. And that comes from a mathematical statement which generalizes the fact, if you have learned about complex numbers, any complex number can be written in a polar form. That is, some real number, the size of the complex number modulus, times e to I theta or something like that. That has something to do with the rotation. But there is a higher dimensional version of this. You don't have to listen to what I'm saying for the next minute or so. So any square matrix has a polar decomposition. This is a higher dimensional version of a complex number. So it can be written as a product of orthogonal matrix and symmetric matrix. Orthogonal part is the e to I theta, and symmetric parts is the modulus. Now, it's much better, now you wake up, you can understand everything that I say. It's much better to see this in a picture. So let's take a square, brown square, and try to shear it into that green parallelogram, okay? You can do it in 2 steps. First, take the brown square, and then stretch it along the diagonal, along the red arrows, and compress it along the blue arrow, and along the anti-diagonal. Having made that rhombus, it's tilted, so you rotate it by a small angle, stonk into place, and the result of that is exactly, or up to higher infinitesimal error, exactly equal to the result of shearing. So I can do the shearing in 2 steps, but the first step that I made becomes really difficult when the Poisson ratio is negative, right? Because when I try to stretch it along the red, it also tries to expand along the blue. Yeah? It does not oblige us by compressing along the blue. So it becomes harder and harder, and Poisson ratio equal to -1 makes it totally impossible. That's why it's the limit. Okay. Now, this is the point to introduce the next dramatis persona, That person, Miura Koryo, Miura sensei, is still alive, and thank goodness. And he's still quite active, actually. He wrote a paper with one of my collaborators at the University of Tokyo last year. And in 1970s, he invented and introduced a beautiful origami pattern called Miura Ori, which is like this. And it has negative Poisson ratio. Let me show you what it's like. Here is the Miura Ori. You know how annoying it is to fold a road map. Oh, wait a second, I said roadmap, but you know, the people in this audience seem to be very young and vigorous. You know that maps used to be made of paper. Do you know this? Yeah. You know, you don't swipe anything. It was an actual paper. I know it's unbelievable, but it's a paper which had sort of place names and sort of drawings and so on. And you opened it while you were driving from Sydney to Melbourne. Yeah? And then, you wanted to know which way to go and so on. And when you opened it, it was perfectly fine. But having checked where you're going, you want to close it and never fold it back in the right way. It starts falling in wrong ways, and it starts making holes, and you go really mad, and then next thing you know, your car is in a tree because you're not driving. And this happens because this usual way of folding a sheet of paper has far too many degrees of freedom. Yeah, you can fold it back in many different ways, but Miura Ori is different. So here's Miura Ori. I fold it like this. And when I compress any 2 points, just mindlessly, it just collapses onto itself. Yeah? And I can just collapse any 2 points, and it just go back and forth, back and forth. It has only 1 degree of freedom. Yeah? It is really remarkable. And also you note that when I compress in one direction, all the other directions compress as well, more or less, statistically, on a large scale. So this has negative Poisson ratio behavior. And indeed, it is true. In Japan, you used to be able to buy such maps. That's a map of near Mount Fuji. And maps in Miura Ori have very few degrees of freedom. In fact, only 1 degree of freedom in most cases. And it's automatically fold because of negative Poisson ratio. Yeah? And by the way, it has also to do with what the geometers called hyperbolicity. I might mention this later on. But anyways, this is a great property of Miura Ori. And I mentioned that Miura sensei is a great man. He's actually an aerospace engineer. And one of the first applications of Miura Ori was realized in the satellite problem. One of the challenges of an artificial satellite is that, of course, after you put it in orbit, you have to supply it with energy. So you have to expand a huge array of solar panels. Okay? And also, it should have a big antenna to communicate with the Earth. But those two things have to be stored in a really tight space in the rocket before you put it in orbit. Yeah? So how do you put something so large into a small space and then expand it in space? Well, once in orbit, do you know what happens typically? So you start expanding this huge gadget and go, clunk, 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 and you get stuck and you have lost $1 billion. And the reason is there are so many points of failure. I mean, it has so many degrees of freedom. But if you folded this in Miura Ori, it has only 1 degree of freedom. It's mathematically impossible to get stuck. So you just grab any 2 points and pull them apart, and the whole structure automatically unfolds itself. And if it possesses you to fold it back again, you just compress them, and it goes back. And this was realized in the Japanese satellite called Haruka, launched in 1997. Okay, so far we have been exploring interesting properties of paper, but they were mostly isotropic, so direction independent. Now I'm going to start exploring things that are direction dependent, and here's what I'll do. I have brought here 2 squares, okay? Here. And they were cut out from a single sheet of printing paper, which I found around the corner from my office at Stanford University. Absolutely nothing unusual. And I assembled them together. I put them together. And then I'll take a paper clip and put them together like this. And then I'll just support them like so on one side. And then, they sag a little bit in gravitational field, but they stick together. Of course, they stick together because they are the same paper. They are twins, if you like. They sag the same way under gravitational field and gravity and so on. But when I turn them over, they separate. You see that? On one side, they stick together. Of course, they should stick together. But on the other side, actually, they separate. So they behave differently, although they are from twins from the same sheet of paper. But that's not all. So this is the separating side, and the other side was the other sort of flipped over, was the sticky side, right? So now I'm going to make my clip migrate to the next edge, and then still hold them on the same side as before. This was the separated side a moment ago, but now they stick together. And what used to be the sticky side on the other side, now they separate. Yeah? So they separate a little bit, okay. Yeah. So it's very, very curious. What's happening? Yeah? It's just ordinary sheet of paper. It works with any paper that you pick. Now, because I like toys, this is a toy, but I brought a toy of a toy. It's a secondary toy, if you like. So if you take a sheet of paper and fold them accordion style like this has the remarkable property that in this direction it bends very, very freely, but in this direction it becomes completely stiff. In fact, it's so stiff that I can support some, this is too heavy, but I can support some weight like this, yeah? It's really stiff. Yeah? In this direction it's bendable, but in this direction it's no longer bendable. Okay. So what I did was the following thing. You go and take your sheet of paper, you cut out 2 squares. Now, sheet of paper has some anisotropy, that is direction dependence. This direction is not quite the same as this direction, but the difference is really tiny. Besides, you cannot see it because it's microscopic. I don't have a microscope, and nobody notices that the paper is different in this direction and this direction, but it's true. So what I did was to cut out those 2 sheets of paper, and I have no idea in what direction anisotropy is running, what direction fiber is running. But it doesn't matter. I cut out 2 sheets of paper. And when I assembled them, I rotated one against the other by 90 degrees. And then watch what happens. If I support them like this, the stiff one is supporting the flabby one at the top, so they stick together. But when I turn over, the flabby one can bend down, but the stiff one sticks out, so they separate. Okay, so that changes the behavior as you turn. And when I support them on the next side, of course, the stiff and flabby one exchange their places, so that's the difference. Okay? So what we have achieved is, in fact, a remarkable thing, which is that microscopic sort of properties we cannot see, but we know that there is some asymmetry, if you like, anisotropy on the microscopic scale. I don't know how. I don't know the direction, but I know that it exists. And just knowing that it exists, I can make the nature play against itself. Yeah? I sort of corner the nature, I dupe the nature into fighting against itself in order to extract the macroscopic behavior that I want. Okay? This is a general principle. You can start from a microscopic thing that you think you cannot control, but by letting nature play against itself, you can extract the macroscopic behavior. So that's what it is. Now, the next example, in fact, examples abound. I went, and probably in the history of the great University of Sydney, it's the first time ever that the public lecturer brings in toilet paper to the lecture. And so this I harvested over there around the corner. It's yours, okay? It's locally resourced. And I noticed that when I tear this paper lengthwise, it tears very, very easily. It's very straight. But if I try to tear it sideways, I try to tear very straight, but I cannot do it. I mean, it goes all over the place. And it really, I'm trying to tear straight, but it becomes this mess. Yeah? So I can tear it in one direction, but not the other. Anyway, straight. And the reason is, this toilet paper also has directional asymmetry, anisotropy, in one direction, in the other direction. The fibers are running probably in a different way. And by tearing, you can visualize it. But this trick is even better. Okay? By the way, I couldn't help noticing also that in this, I emphasize the locally resourced paper, which is from the University of Sydney. And this toilet paper tears very easily lengthwise, but not across. Okay? You should think about this. Okay? It's something very, very deep going on. Okay, so let's now go back to geometry and then do something really fancy. Okay, so let's consider the following funny problem. Here's a large spherical shell. By the way, when a mathematician talks about a sphere, they really mean a spherical shell, the two-dimensional thing, yeah? And when they want to mean something that is solid with the interior fielding, they call a ball. Okay, so I might actually slip into that distinction, but when I say a sphere, it's really a spherical shell. So let's take a spherical shell, an ordinary two-dimensional spherical shell in our three-dimensional space, and the question is, can you actually sort of, it's made of some material, can you actually forcibly put it into a small space? And the answer is yes, you just squash it, yeah? But now, can you do it isometrically, that is, without changing any length on the sphere? And the answer is that you cannot, because when you try to squash it, you surely have to dent it like this. And then something called the Gaussian curvature gets in the way. Gaussian curvature is the way that we mathematicians have invented, in fact, Gauss himself invented, of measuring how curvy some surface is. So it turns out that the sphere has Gaussian curvature, which is positive, it's positively curved, and it turns out that 1 over radius squared is the formula. But when you dent it, you create something like a crater, okay? And the ridge of the crater is actually a part of the circle which has 0 Gaussian curvature. So the Gaussian curvature used to be positive, but now there's a part which has 0 Gaussian curvature, and really the surface doesn't like it. It's extremely costly in terms of energy to do this. So Gaussian curvature is an isometry invariant. In other words, if you keep track of, if you preserve all the lengths are equal before and after the transformation, then the Gaussian curvature must stay the same at corresponding points. So because you change the Gaussian curvature from positive to negative somewhere, this cannot be an isometric transformation. You cannot put a large sphere into a small sphere isometrically. That's not possible because Gaussian curvature gets in the way, okay? Without stretching or shrinking the surface. However, mathematicians are very bad losers. So we say, if you come to University of Sydney and take a course in geometry, differential geometry, you learn the Gaussian curvature, and also you learn how to compute it. And it turns out that you use calculus to do this. And in calculus, there's a famous concept of derivative. It turns out that the formula for the Gaussian curvature involves 2 derivatives. So you differentiate something and you differentiate it again, second derivative. So maybe you start saying, this really sounds like a desperate attempt. Maybe you can try this sort of squeeze into a small space. We're using surfaces that have only 1 derivative. In other words, smooth but not that smooth. You can differentiate only once. Because then what you're going to have is that when I say, well, I can put it in a small space, Professor Williamson will say, but Tadashi, you cannot do this. Gaussian curvature gets in the way. But I say, well, what Gaussian curvature? I have only 1 derivative. You cannot compute the Gaussian curvature. I mean, this sounds like really a cop-out. But in fact, it works. The greatest minds of the century, like Nash and Gromov, prove the existence of this isometric embedding into a small space by using C1 but not C2. That is, surfaces that are smooth but not smooth. Yeah? It's really a strange thing. But more recently, a French team, including Borelli and Thibert, and so Borelli came to show me this picture, or in fact show me an actual object some time ago, realized what was only an existential theoretical construction by Nash and Gromov. By the way, Nash is the Nash of Beautiful Mind Nash. Yeah? I used to know him at Princeton. So they actually, this French team, realized a concrete way of doing it. And I say concrete because they made this model with concrete. But anyway, so it's as you can see, the first step is to take a sphere and then kind of globally twist it. Yeah? And when you twist, you get those strange corrugations. But the point is that when you see under microscope each of the corrugations, each corrugation is lined with more corrugations of the intermediate scale. And each of those intermediate corrugations, if you look really closely, is corrugated by smaller scale and so on, all the way by scale invariance, all the way to 0 scale. This is really a very, very strange picture. And when Borelli showed me this, I said, I have seen it before. Because it is what I call a twisted version of Miuraori. I'll show you one beautiful buckling pattern which can be produced as follows. Take a sheet of paper. All my experiments start with take a sheet of paper. And you take 2 straight glasses, yeah, completely straight, it doesn't fan out and so on. And then you put them facing each other with a little bit of gap in between, okay? And having done so, you roll the paper around those 2 glasses, and then grab this, and then twist those glasses against each other, and then squeeze. Okay? And then when I see what has happened, you see this really strange pattern. You can see? Yeah, so this kind of wavy pattern from the other side is even better in the shadow of the sort of setting sun against the mountains. And all this geometry of this sort of angles and so on is determined completely by one dimensionless parameter. That is the ratio of how much the gap there was between the glasses and what's the diameter over what's the diameter. So gap over the diameter, that one number, which doesn't have any dimension, pure number, determines the entire geometry. Okay? So this is real. And you see, this pattern, if I ever saw one, is actually the same pattern as those corrugation patterns. And for a good reason. It's the same pattern because what did I do when I did this twist buckling? Well, I put paper between those 2 rims of glasses, and I asked nature, I want to actually you to squeeze this into a tighter space, tighter and tighter space. And nature has to do something. Nature doesn't want to do anything non-isometrically because it costs money, it costs effort. But I'm forcing it to do it. And when I squash, it just gives up and creates those singularities. So this is nature's way of isometrically embedding, if you like, some sheet of paper into a small space. And this is, of course, what happens. In other words, you see, Bulgarian and Tibetan national group of wonderful people, very, very smart and very hardworking and very inventive, but we didn't have to actually invent anything. We could have asked nature to do it. Yeah? And this is one thing that I would like to advertise. It's very interesting to do this kind of thing by asking nature. So next thing. It's slightly off the topic, but it's still related. I would like to show you another origami, which was invented by another aeronautical engineer and called Momotani, a Japanese one. And this thing is made of a single sheet of paper. So about a year large, so it's a special sheet of paper that I had to get. And on a long, long flight, not as long as the flight that took us, me and my love, from San Francisco to Tokyo to Sydney, but on a long flight which lasted for maybe 10 hours and so on. I took a sheet of paper and settled myself. And when we took off, I started folding this sheet of paper. And then my neighbor looked really worried about this. And there's some coffee stain and so on. But anyway, what happens is this. So I folded this sheet of paper into one, and this is the object. When I pull in one direction, watch what happens. I'm going to try to do it in a direction which is a little less glare. This is what happens. Whoop, whoop, whoop. And if you look at the other side, it's dual to, it's perpendicular to what's happening in front. Yeah? So this is really a fantastic thing. And you can see that it has negative Poisson ratio in the sense that when I pull in one direction, it expands in the other direction as well. But moreover, this is really a digression. It really has another amazing effect, amazing property, which is that, this is made of sheet of paper. Paper doesn't have elasticity. It's not like rubber. But this, if I pull and release, it's just bouncy. Yeah? So this is an interesting way of doing origami, which endows paper with the bounciness, with rubber-like elasticity. That's really curious, okay? Anyway, so it's another example of negative Poisson behavior. Oh, thank you. I like you like. So it's time to wrap up all this discussion. So we saw many, many examples of negative Poisson, and including last two. So twist buckling produced this, but that's negative Poisson because you compressed in one direction, you compressed in a gas direction, and also Momotani carpet. So all of these are actually, in some sense, variations of or are based on Miura-Ori. Yeah? So I'm going to tell you what's special about Miura-Ori. Here is the simplest Miura-Ori where it's characterized as two numbers. Let's say that for simplicity, each panel, if you like, of Miura-Ori, this folding pattern, has all the edges equal. Yeah? So it could be a kind of parallelogram in general, but I'm talking about the rhombus, so that all the edges are equal length. Then it's characterized as two numbers. Alpha is the corner angle. So if alpha is, say, 90 degrees, each panel is a square. Okay? And if alpha is very small, each panel is long and thin. All right. And then the angle theta, this is dynamic angle, which just indicates the angle between two adjacent panels. So if theta is, let's say, 180 degrees, that means that the whole thing is stretched flat. But when theta becomes smaller and smaller, everything is collapsed into the smallest configuration. So, and in that configuration, so let's say Miura-Ori has some fundamental angle alpha, and in the state which has angle theta, it's easy, actually, in that state to calculate the Poisson ratio. And the calculation gives you this. Poisson ratio equals 1 minus something there. And if you know about sine functions, you see that that something is larger than 1. Yeah? It's 1 over something smaller than 1, so it's larger than 1. So I'm subtracting something larger than 1 from 1. So that's a negative number. So it has a negative Poisson ratio, which you knew, because in Miura-Ori, when you compressed in one direction, you compressed in the other direction too. But what is amazing is that, again, if you know anything about sine functions, by playing with numbers alpha and theta, you can see that actually you can hit any given negative real number. Yeah? So it turns out that if you give me any negative real number, I can realize that number, negative number, as the Poisson ratio, negative Poisson ratio over Miura-Ori. At this stage, some of you might remember the theorem that I mentioned about Poisson ratio being between -1 and +1/2. So you cannot go below -1. What about that? Well, that was a theorem about isotropic structure. This is anisotropy because Miura-Ori has a very, very distinguished sort of axis direction, of course. So in the presence of anisotropy, you can actually get all the way down to negative infinity. So negative Poisson ratio really in the strongest sense. But that's not all. You remember that we mentioned and we showed you the buckling of a rod. That was one-dimensional buckling, and this was understood by Euler a long, long time ago in the 19th century. But you can try to do two-dimensional buckling. This is more exciting stuff, but much harder to do geometrically and also experimentally. What do I mean? Let's take a sheet of paper or membrane and try to apply compression, homogeneous and isotropic compression at all the points at the same time. How do you do that? It's very difficult to do experimentally because if you start pushing the edges, the boundary effect becomes really dirty. So I would say you should use moisture or temperature. But anyway, you try to compress. And it turns out that for small compression, gentle compression, initially the entire membrane becomes smaller in area along its own plane, like the rod. Yeah? But at some point, the membrane cannot take it anymore, and boom, buckles in the transverse three-dimensional direction. And that buckling pattern creates a wave, and that wave pattern, ladies and gentlemen, boys and girls, is actually Miura-Ori. So it's the lowest energy mode of a buckling, two-dimensional buckling pattern. So this is really an amazing result, which means that you see Miura-Ori I introduced to you as a very beautiful origami pattern, but it's not just a special thing. It turns out to be, Miura-Ori turns out to be simplest and actually universal model of negative Poisson ratio. Yes. At that stage, I realized something. Until now, I have been really working hard, and so have you, in sort of designing something that has negative Poisson ratio and how to fold, and you have to do a precise experiment and so forth. But it turns out that there's a much, much easier to produce negative Poisson ratio materials. And that is to just crumple a sheet of paper. Take a sheet of paper, and let's crumple it like this. I'm not doing anything special. Yeah, okay. And then when I pull it in one direction, look, it starts expanding in all other directions. That's negative Poisson ratio behavior. And of course, because I made it that way, I just compressed it in all directions, more or less equally. And so when I try to undo it, it expands in all different directions. Yes, okay. So you are going to complain that if you have a bird's eye view, that's true. But if you look sideways, when I compress, actually it gets, as it gets crumpled, it gets a little fatter in the transverse third dimension, right? But actually, that's okay. That's innocuous because you can take any gap between the top surface and bottom surface, ceiling and floor, let's say, of gap epsilon. And if I increase the wave number, if I crumple a lot, I can keep all the crumpling in that gap. So quantitatively speaking, for any allowable small epsilon, I can actually do it within epsilon. So it's basically successful negative Poisson ratio behavior. So crumpling a sheet of paper. And look, if anything, this looks very, very random, doesn't it? Yes, to be precise, I mean, it's satisfying that famous theorem about alternating sum equals 0. But apart from that, it's really as random as humans can imagine. So it turns out that, in fact, just crumpling a sheet of paper does, randomly crumpling a sheet of paper does produce negative Poisson structure. And it's homogeneous and isotropic on the large scale on average statistically. So I have a bold conjecture written in bold besides. Until recently, people thought, well, negative Poisson, Poisson ratio should be positive always. But so negative Poisson ratio doesn't exist. But if it existed, it's really freakish. You have to be really clever and really perverse to be able to produce it. But far from it, it might be that randomly generated structures in the universe might have negative Poisson ratio in the majority of cases. That would be really interesting. It is time to wrap up this lecture. And in doing so, I'd like to sort of muse on science in general. You see, all of us scientists, practicing scientists, as well as the general public and policymakers and everyone else, seem to have the impression that science is practiced in a very specialized context, yes? So, yes, science happens in laboratories, yes, and institutes like this one and so on. And you collect the information on the internet and in journals, which are housed in libraries, and of course classrooms where you go listen to professors and fall asleep, and you have big research grants that you have to have in order to run the lab and so on. And in order to do so, you have to get submit cutting-edge proposals to various funding agencies and so on. And all of these are, of course, part of the industrialized, all huge societal ways of organizing science. And we kind of live off it, right? This technology science-driven society. These are therefore all supremely important because that's where we expect science to come from, yes? It has to be big, it has to be completely organized, it has to be totally professionalized, it has to be specialized, yes? So you are absolutely justified to ask me, Tadashi, why are you playing with paper against this? So by way of an answer, I'd like to share with you a very little read passage in Aristotle, of all people. So Aristotle wrote many, many interesting books. Some of them are actually not that interesting. But this one is interesting, De Paritibus Animalium. By the way, this is Diels und Kant, which is the For Socratica, the largest collection, most authoritative collection of pre-Socratic philosophers, and actually includes tales of pre-Socratic philosophers told by post-Socratic people. But anyway, this is number 2289. And Aristotle in this passage tells the story of Heraclitus in Greek. So this was the pre-Socratic philosopher who flourished around 600 BC or so. And he's the one who said, Pantare, everything flows. And he had lots of interesting ideas. If you like, he was kind of the a superstar of science at that time. Natural philosophy was called, equivalent today of, say, a professor of mathematics at University of Sydney, okay? So everyone knew about this man, everyone was following him and his musings and his discoveries with excitement. And one day, the story says, 2 young people came to visit Heraclitus, okay? And they were really excited to see this superstar of science. And then they were expecting some picture of Heraclitus. They thought probably Heraclitus was wearing a lab coat with a long white beard and probably sitting on the console typing in some complicated code into a supercomputer and probably running a huge lab with sophisticated equipment with hundreds of postdocs and so on, and maybe lecturing to hundreds of people in a large auditorium, et cetera, et cetera. Yeah, that's what a great scientist does, and of course that's the caricature of Heraclitus. But Aristotle says, when those 2 young people arrived at Heraclitus' house, they saw a completely different Heraclitus. And they were really surprised. This is Aristotle speaking and my free translation. In all natural phenomena, there is something of the marvelous. There is a story that some visitors once wished to meet Heraclitus. But when they entered and saw him in the kitchen, warming himself at the stove and playing with the children, they hesitated. What, is this the great Heraclitus? What's this guy doing? I mean, he's supposed to be a great scientist, and he's supposed to be doing all those things that, where we expect science to come from. But Heraclitus said, come in, don't be afraid. There are gods even here. Come in, don't be afraid. There are gods even here. Enagar kai entaitha theus. It's been a great pleasure and privilege to address this audience. And especially I'd like to thank Professor Stefan Tillman and all my friends, new friends at Sydney, and at the those at SIMRI for their very, very kind invitation. Thank you very much.